Thank you very much. Assalamu alaikum and good morning. Good afternoon, everybody. My name is Adeel Faisal, and I'm a Ph.D. scholar in the Department of Civil Engineering. My research supervisor is Dr. Safir Abbas, and post-supervisor is Dr. Ali Engr. The title of my research is Structural Performance of Spun Cast Full-Scale Reinforced Concrete Pipes Incorporating Hybrid Fibers. These are the contents of my presentation. Water is a basic necessity of life. However, when consumed, it turns into wastewater. Now, wastewater requires safe disposal. If not properly disposed, it poses threat to the environment and causes the spread of various diseases such as diarrhea, typhoid, etc. It has been estimated by WHO report that insufficient sanitation has an impact of 343.7 billion rupees on the economy of Pakistan. This research is directly related to 3 Sustainable Development Goals: SDG number 3, Good Health and Well-being; SDG number 6, Clean Water and Sanitation; SDG number 11, to make cities sustainable and resilient. At national level, the National Sanitation Policy by Government of Pakistan aims to provide 100% sanitation coverage to all by 2025. However, the current situation rather looks grim. According to Pakistan Bureau of Statistics, only 22% population of Pakistan currently have access to a sewage network, which means the sewage network needs to be expanded. According to a UN report, an investment of $1 in sewage infrastructure results in $4 in saving. And these concrete pipes are important components of a sewage network. Concrete pipes are manufactured mainly by 2 methods. One is the vibro compression method and the other is a spun cast method. This vibro compression method is usually practiced in developed countries. The compaction is achieved through intense vibrations in automatic plants, and the demolding can be done immediately. However, the locally practiced method is different. The steel cage is inserted into the mold, and the end rings are attached, and then the mold is placed over the rollers. The concrete is mixed through drum type mixers, and it is handled and placed in the molds manually through shovels. So this is the dry cement added at a later stage for finishing purpose. The extra concrete needs to be scrubbed, and the inner surface needs to be polished. So when the spinning is stopped, the mold is taken off the rollers, and the demolding is done after 24 hours. Conventionally, concrete pipes are reinforced by a steel cage consisting of circular bars and longitudinal bars. And the testing is done according to 3 edge bearing tests according to ASTM C497. And the crack needs to be monitored continuously using a crack gauge like this, so that the maximum load before the crack width reaches 0.3 millimeter has to be recorded. Now during the test, some regions of the pipe are in tension, shown in red color, and the other are in the compression zone, shown in blue color. Now if you can see, the tensile stresses occur on the inner side at these locations, the crown and inward, and on the spring lines, the tensile stresses are now on the outer side of the pipe, which means ideally we would require 2 steel cages, one to resist the inner tensile stresses and the other to resist the outer tensile stresses, so a double cage is preferred. However, in small diameter pipes, the wall thickness is too small to accommodate 2 layers of reinforcement, so that's why just 1 layer has to be provided, and that is positioned at near the mid thickness level, where it would be least effective because that's where the needle axis would be expected. This is a quick overview of the literature that I've reviewed. Several researchers have attempted to study the performance of fiber-reinforced concrete pipes manufactured using either vibro compression method or in some cases Packer head method, and the investigated fibers are either steel fibers or synthetic fibers in monoform, and most of the results conclude that fiber-reinforced concrete pipes can be an attractive alternative to the traditional reinforced concrete pipes due to superior crack resistance. Some more studies incorporating PP fibers, and then one more study on the hybrid fibers, but then the fibers used are basalt and PP fibers. Now, based on the literature review, we came to see that the previous studies have been focused largely on either the vibro-compression method or the peckerhead method, and the spun cast method is rarely explored. Moreover, these hybrid fibers are not explored in detail especially the combination of steel and synthetic fibers. So this study is aimed at structural performance of spun cast hybrid fiber reinforced concrete pipes. Now, concrete pipes are always buried structures. Now, this means when the cracks appear, they are not visible, which means the failure is apparent only when this happens. The road collapses or the settlement takes place due to leaking wastewater. Now, this means that the crack resistance has to be improved for the concrete pipes, because once it's put into the place, the chances of remedial measures are limited. Moreover, the fabrication of conventional steel cage is time consuming. In a sense, the steel coils, they are cut into straight lanes, bent into circular shapes, and then each circular bar the ends have to be welded. And then this is how one circular bar is formed, and then there are about 30 to 40 circular bars in one pipe and 6 longitudinal bars in one pipe. So the cage fabrication then the circular bars have to be further welded with the longitudinal bars to make the cage stable. Now this is a production timeline of a typical 300 millimeter diameter pipe. This is the time lapse in minutes, and these are different activities to produce the pipe. As can be seen, this cage fabrication takes a significant amount of time, and if this can be eliminated using any alternate reinforcement, the production efficiency can be significantly enhanced. Moreover, the testing of conventional RC pipes is dependent on human judgment. Imagine an operator, or in fact a group of operators, waiting for the crack to get wide enough so this gauge can be inserted. Now, then obviously it's a subjective method. One operator may miss the point where the crack was just 0.3 millimeter, the other one may or may not be able, and it's dependent on the ability of the operator. So this is quite subjective, and it should be a more rigorous or scientific method. This is a clip from one of the testing. This is how the gauge has to be inserted and the load has to be recorded at this point. Now, these are the specific research objectives in order to address the problem just discussed. So first is the assessment of local manufacturing practices of precast concrete pipes and their mechanical performance. Second is the development of concrete mixtures incorporating various types of fibers for the spun cast concrete pipes. And thirdly, to investigate the structural performance of full-scale spun cast concrete pipes incorporating various types of fibers and steel reinforcements under various loading regimes. Fourth is development of rational design guidelines for fiber-reinforced spun cast concrete pipes using three-dimensional finite element analysis. And lastly, to quickly revisit existing ASTM standards such as C76 and C497 and local design guidelines on concrete pipes. This is a brief of the overall research methodology taken in this research. Industrial visits in the first phase, followed by pilot study and full-scale 450 millimeter diameter pipes, mechanical properties of fiber-reinforced concrete mixture through various tests, and then full-scale pipes once again on 300 and 750 millimeter pipes, and finite element modeling in the end. So I visited several industries and government departments for exploring the problem related to concrete pipes, and also various places or sites of crack failure, the pipe failure. This is crack pipe being replaced at Jail Road, another failure at Mall Road. And then finally, the detailed exploration was done at 6 local pipe factories. I had to conceal their name based on their request. So this is just labeled as A, B, C, D, E, F. These are actual factories. The local concrete mixture proportion was detailed. This is the weighing balance, digital weighing balance, to accurately see what proportions are being practiced, and the casting of cylinders at local factories, and then testing the cylinders in the lab. Since as I will discuss in detail in the research section, the compressive strength of concrete practiced at these local factories was much lower than what is the minimum requirement of 27.6 megapascal. Therefore, first a concrete mix was designed according to the guidelines of ACI 211.3R. This is the summary of the mix design that was designed. And these are the results of the trial mixture which confirm the mix design. This is test metrics for a pilot study on full-scale 450mm diameter pipes, various types of fibers with plain concrete, steel fiber, 2 conventional reinforced concrete pipes, and these 2 pipes have the conventional reinforcement as well as have the steel fibers. So the straight steel fibers were used in these, and this last pipe was cast in layers because segregation of steel fibers was observed when the casting was done for the above pipes. So an attempt was made to control that problem, but anyways, I'll discuss the results in the relevant section. This was done to see what is the rotational speed of the pipe during the manufacturing process. So you can see a blue tab is attached, and the whole spinning the manufacturing process, the video of this was recorded. Now it was too fast to count the revolution, so it was played in slow motion. And then the rotational speed in RPM of the mold against the time was plotted. You can see the pouring of concrete is the first phase, and then when the pouring is finished, the speed is enhanced to achieve the compaction. So this is the test conducted on the pilot study, 3 edge bearing test. This is the physical model of the test. Upper bearing and 2 lower bearings, and the pipe is loaded from the top. The other test is a modified form of 3 edge bearing test, with the difference that the load is applied on mid-length of the pipe instead of equally uniformly distributed load over the pipe. So various types of fibers were investigated in this phase. This is straight steel fibers, bundled steel fibers, and PP fibers. These are the different properties that were obtained. Some of them through the tension test, and the other were measured. So this is a close-up view of the bundled steel fibers. You can see how this one fiber unwound into these individual wires. So this is the test metrics for the exploring the mechanical properties of various fiber-reinforced concrete mixers. A total of 16 different mixers with control mixers of the plain concrete, straight steel fibers, bundled steel fibers, PP fibers, and hybrid of bundled and PP fibers at various dosages. And the third phase was the casting. So this was the casting and testing of fiber-reinforced concrete mixers. The cylinders and the prisms were casted in the lab and tested under compression, splitting tensile strength, and the flexure test according to the relevant ESTM standards. So this discusses how the pipe diameter was selected for the rest of the pipe. An analysis of the data available at test floor lab here in UET. We could see that most of the pipes were in the range of 225 to 300 millimeter smaller diameter pipes were in high demand, and therefore these 300 millimeter diameter pipes diameter was selected as 300 millimeter for this study. Sorry. So the next was the selection of fiber dosage, and it was a rationale. The rationale was the moment capacity of the fiber reinforced section should be at least equal to the moment capacity of the RC section, and the required flexure strength was worked out, and this strength could be easily achieved by using the fiber dosages shown on this next slide. So this is the full test metrics for the full scale 300 millimeter diameter pipes. Different pipes, again pipes were tested: plain concrete, reinforced concrete pipe, 3 different types of fiber reinforced concrete pipes. The loading was different, continuous loading according to these 2 standards, C497 and C1818. And this C1765 requires loading the pipe up to the crack load and then unloading it and then reloading the pipe to test the effectiveness of the fibers. So the hybrid pipes, there is currently no ASTM standard on hybrid fiber reinforced concrete pipes. So therefore these pipes were tested according to both ASTM C1818 and C1765. So this test metrics for 750mm full-scale pipes. Again, 3 types of pipes were investigated. RC1 was the control specimen, and RC2 and RC3 had reduced reinforcement, 75% and 50% of the control specimen. So now the wall thickness was large enough for these pipes, so the double reinforcement was provided in these pipes. And not only the lab investigation, but also field investigations were conducted. So the pipes were installed in the field, and various types of vehicles available at the site, such as transit mixer, dump truck, roller, and other vehicles. They were passed over the field buried pipe, and the deflection was recorded. This is schematic of the whole setup. And lastly, the finite element modeling. The geometry and boundary conditions are shown here. The bottom was restrained and the top loading was applied to the top to replicate the experimental setup. These are the constituting models that were used: Thornfeld for compression, Haldane for tension, and Nikawa for the steel bars. These are the different parameters used to define these models. And for the fiber reinforced concrete, ACI 544.8R model was used, and accordingly inverse analysis from the flexure test to this model and then introducing of spinning factor. So this summarizes the parameters used to define these continuity models. Since finite element analysis depended on the mesh size, so it was required to first perform a mesh sensitivity analysis. So therefore, different mesh sizes, 15mm mesh, 20mm mesh, 25mm mesh, and 30mm mesh sizes were investigated. This is for 300mm pipe. And compared with the experimental data, it could be seen that 15mm and 20mm pipes, these mesh sizes provided close simulation of the experimental data, and 15mm mesh size was used for the smaller diameter pipes and 20mm for the larger diameter pipes. So this quick summary of what was done in the methodology, industrial visits, pilot study on 450mm, and the mechanical properties of various reinforced concrete mixtures, and structural performance full scale, laboratory testing, field testing, and then the finite element analysis. So these are the results and discussions. First for the objective number one, which is the exploration of local factories. So these are different factories visited, A, B, C, D, E, F, and then these are the mixed proportions practiced in these factories. What one can find that the water cement ratio is significantly high, and this is the reason the compressive strength is much lower than what is minimum required by ASTM C76. And then it was compared, you can see the comparison with a design mixture. Much lower water cement ratio can be used, it has to be provided in order to achieve that strength. So these are the results of the pilot study on 450mm diameter pipes for the 3-8 bearing test and for the pass-out test. On horizontal axis, this is displacement, vertical displacement in millimeters at the crown, and this is the load in kilometer on the vertical axis. This is just a magnified view of the initial part to clarify the initial graphs over here, separately same goes for here. Now, as can be seen, the PC pipe collapsed in a brittle manner. The SFRC provided some resistance to the cracks, but the improvement was minimal. And the RC1 and RC2, these were the conventional pipes. RC1 class 2 pipe, RC2 is class 4 pipe. The RC2 pipe had higher load capacities as compared to RC1 pipe because of more reinforcement put into RC2. This RC1 and RC1 SF1 and RC1 SF2, these two pipes had conventional reinforcement equivalent to RC1, as well as fiber dosages of 20 kg per meter cube and 40 kg per meter cube. Now this conversion can be seen, the red and the black line, so the improvement that you can see is not very significant for the RC1 SF1 pipe as compared to the RC1 pipe. And however, for the RC1 SF2 pipe, which was cast in layers and had 40 kg per meter cube of steel fibers, had a considerable improvement comparable with the RC2 pipe. The results of Faisal test were largely similar, with the difference that the load was slightly lower as compared to the 3 bearing test because of the concentrated loading applied on the pipe. Now, this explains why steel fibers were not effective in improving the performance of the pipe. So you can see this is the pipe tested, and this is the spring line side, on the outer side, the crack appeared, the steel fibers braided. This is the inner side, the inward of the pipe. The steel fibers had segregated towards the outer side, so no fibers were available to bridge the cracks on the inner side. What clearly shown over here on the fractured surface, this is the outer side and this is the inner side. The steel fibers could be seen roaming in the outer side. So when the crack appears on the inner side, this happens at the inward and crown, no fibers were available to intersect these cracks. So the problem in the pilot study that was identified was the segregation of the steel fibers, and this was the stage when the PP fibers were considered for inclusion in the study. Now this is the development of concrete mixers. So these are different properties for the fiber reinforced concrete mixers. First, for the slump. The slump gradually decreased as the fiber dosage was increased for all types of fiber reinforced mixtures. Compression strength was largely insult sensitive, but it could be seen that the bundled steel fibers had a better performance compared to the other, but still the improvement was just minimal. And what we can see over here is the change of failure mode. This is PC pipe, you can see the failure is abrupt. This is the fiber reinforced concrete pipe, which shows gradual failures with distributed cracks over the cylinder. These are the results for the splitting tensile strength. Again, the strength increased with the addition of the fibers, and you can see the fibers are holding the cylinder from going apart, even at very large crack width. Even the loading assembly slumped into the crack, but the cylinder was still ensuring the integrity. Now these are the flexure results from the flexure test. This is deflection on horizontal axis, and then the load is on the vertical axis. Different types of fibers. So you can see the bundle steel fibers were more effective than the straight steel fibers. The PP fibers had compared slightly lower peak strength, but the residual strength was higher than the steel and steel fibers. The hybrid fibers provided better than all, in a sense that it had good peak comparable with the steel fibers, and also high residual strength. So these were quite recommended for the production of full-scale pipes. You can see the cracks appearing. Initially a hairline crack appears, and then it starts widening in the cracks the fiber. This is at the very later stage of the testing when the fibers are fully exposed. So this is the result for the 300 millimeter full-scale pipes, in which 5 different types of pipes were tested under continuous loading and 2 tests under the loading and ring loading. So you can see the hybrid fiber, this line, the blue line, which represents the hybrid fiber reinforced concrete pipes. It had very significant improvement compared with the other pipes, followed by the PP fiber reinforced concrete pipe. And this steel fiber, again, when they were used alone, they were not very effective. So this is just the magnified view of the same graph for the initial part to clear what's happening in this region. This is the loading. This is the loading to the hairline crack position, and then the unloading to 0, and then reloading. Now this reloading phase actually tests the pipes, the effectiveness of the fibers, because now concrete matrix is already cracked, so the resistance is coming primarily from these fibers, and the hybrid fiber reinforced concrete pipes could still bear a significant amount of load even when the crack had already appeared. So these are different cracks that appear in more detail on the next slide. I'm sorry, yeah, so the black is the steel fibers and the white is the PP fibers. I just wanted to show you in a demonstrative way what happens during the spinning. Steel fibers are high specific gravity materials, PP fibers are lower specific gravity materials. So when spinning takes place, steel fibers moving outward and PP fibers going inward. So this effectively acts as 2 layers of reinforcement, just analogous to 2 layers of reinforcement, which can take care of the cracks appearing on different locations. More detail on this slide. So this is for the steel fiber reinforced concrete pipe, this is for the PP fiber reinforced concrete pipe, and this is for the hybrid fiber reinforced concrete pipe. What we can see again over here, spring line, fibers are bridging the crack, inner side, no bridging. PP fibers could bridge the crack on the inner side as well as the outer side. This was a little surprising, but it's what we observed in the experimental test. And the hybrid fibers had the best performance. Steel fibers taking care of these cracks on the spring line, which appears on the outer side, and the PP fibers taking care of the cracks on the inner surface. So this sums up the difference between an FRC pipe and a conventional RC pipe. The red line is for the FRC pipe, the black line is for the RC pipe. This is low deflection curve. An RC pipe would usually go through 3 stages for failure to happen. First, a hairline crack would appear, and then it has to be monitored using this gauge to see when this gauge can be inserted to note the load corresponding to 0.3 millimeter crack, and then at the ultimate stage, of course, the crack width is much larger than 0.3 millimeter. However, FRC pipe has different failure ways. It goes to the ultimate and where a visible crack would appear first, and then if the load starts going down, let me show you what happens exactly. This is how the crack just appears, and this is what this part of the load deflection diagram corresponds to that stage. You can see the different operators trying to work. You see the crack is wide enough. Now, this stage where the crack reaches 0.3 millimeter occurs after the ultimate load point. Now, the definition of 0.3 millimeter crack load according to ACMC 822 is it is the maximum load supported by a pipe before a crack having a width of 0.3 millimeter occurs. Now, what does this mean? This load is not the 0.3 millimeter, the blue dye. This load is because this is the maximum the pipe achieved before the crack could get to the limit of 0.3 millimeter. So that means for FRC pipe, this 0.3 millimeter crack load is equal to the ultimate load, which means you would no more have to gauge the cracks because you can record this ultimate load from the machine and you can can eliminate the subjective decision of crack gauging. Just for to give a broader context to this study, comparison was done with a variable compression based study conducted by Muhammad, although this study was not conducted in Pakistan, just to clarify. The strength in these pipes, the capacities was way higher compared to the pipes in this study, and this is the reason. Muhammad casted pipes with larger wall thickness, lower water cement ratio, and much higher concrete strength, and used variable compression method. This also signifies that the concrete mixture and the manufacturing method are key factors that affect the performance of the pipe. This is the results for the live loading of field buried pipes. The pipes were buried as I discussed, and we could see no crack appear on these pipes. So the same pipes were then transported to the lab. These are results from the lab test. This is the field buried test, and this is from the patch load test. RC1 had better performance, obviously, because of more reinforcement. As the reinforcement was reduced, the performance also dropped. With again the patch load further dropped because of the concentrated loading, and you can see this. This was where this is after testing picture. So this is where the patch loading was applied. You can see a localized damage. Now, just to investigate one more thing that we have in the local guidelines, it says the Public Health Engineering Department guideline says a minimum of 3 feet earth cover has to be provided over any concrete pipe. Now, I tried to investigate if this 3 feet pipe could be reduced using computations based on American Concrete Pipe Design Manual, ACPA. Now, this is a comparison between 3 feet bureau depth, and this is for the 2 feet bureau depth. The various loads were computed, and you can see that this required load to be resisted by the pipe, 69 kilonewton. This is for 300 millimeter diameter pipe, just to clarify. This load could be easily achieved even by conventional pipe. So I believe this could be reduced to 2 feet. However, more investigations such as experimental investigations may be required to further back up this conclusion. But however, just for context, ASCE 15-17, it requires the minimum concrete cover of 1 feet, minimum earth cover of 1 feet. So currently we are at 3 feet. I believe we can gradually come down to 2 feet and maybe then lower. So now, what is the benefit of reducing this to 2 feet? You will need less excavation. You can save costs on less excavation because you have to do less excavation. Now, finite element modeling, the results of the simulation are presented for the 300 millimeter pipes. As can be seen, these model could effectively simulated experimental results, and you can see the vertical deflection come through over here. The blue lines, the negative sign means its reflection is downward. You can see it's most blue at the top because it is happening from the top. The bottom is nearly red, which means because it was restrained. Again, for 450 millimeter diameter pipes, the simulation was done, and this is for the 750 millimeter pipes. So I will just show you not only the low deflection curves were simulated, but also the crack pattern was simulated. This is a crack pattern experimentally observed, and this is a crack pattern from the finite element model. This is actually the crack strain that appears. Now, the reason for the cracks appearing at these locations is explained by what you see over here for the principal stresses. The red lines show the highest regions of tensile stresses, and this is the region the cracks appear at these locations in the pipe. They originate from these locations. Just a few more details on what this is the complete load deflection graph, but I would just point out 2 points. That the model could find out the crack width corresponding to each load step, and this is the step at which the load width was exact, the crack width was exactly equal to 0.3 millimeter. At this stage, you can see the steel bars are not yet yielding because you can see the maximum stress is 270 megapascal and the yielding strength is 457 megapascal. So at this stage, the steel bars are not yet fully accumulated. However, further down the line, you can see at this stage the crack width is moved to 0.7 millimeter, and the steel stress is now 463 millimeter, higher than the yield strength. You can see these red dots showing the points where the steel has locally yielded. Even further computational work based on the recommendations of the external examiners. So the theoretical equations were also developed in order to predict the capacities of these pipes using theoretical equations. So the theoretical equations would could give an estimate which was slightly on the conservative side as compared to the experimental results, which means they could be used for design purpose. Now this summarizes the proposed reinforcement for different diameters of pipes. For diameters up to 375 millimeter, PP fibers are recommended. This has an advantage that smaller pipes have lesser wall thickness, which means if any metallic reinforcement is provided, it is susceptible to corrosion and the reinforcement may be corroded and it could be a durability problem. So these PP fibers being non-metallic were recommended as the first resort. As the diameter increased, hybrid of PP and steel fibers were recommended, and then for the larger diameter pipes, the results showed that conventional steel cage, because now the wall is thick enough, it can be provided for these pipes. Just to give investigate the economic feasibility, a cost comparison was done. This is detailed comparison for 300 millimeter diameter pipes. It can be seen that the comparison shows that the FRC pipes are comparable to conventional pipes as far as the 300 millimeter diameter pipe is concerned. This is summary for some other diameters of pipes. As you can see, as the diameter of the pipe increases, the conventional RC pipes become more viable. So that's why this research also, one of the reasons for limiting the FRC pipes to the smaller diameter is because of the cost factor. Quick comparison of the benefits: crack resistance is higher for the FRC pipe, corrosion resistance is higher for the FRC pipe. If PP fiber is corrosion free, if it is hybrid PP and steel fiber, still the corrosion potential is lower for the fibers as compared to a continuous steel cage. Manufacturing is less labor intensive for the FRC pipes because cage fabrication is eliminated. Testing is even more, this has a subjective testing criteria which could be eliminated if the transition is done to the FRC pipes, because as I discussed, it doesn't require gauging the crack. And one challenge that we faced with the PP fibers coming towards the inner side was it rough on the inner side, and this means some more measures would be required, such as coating, in order to achieve better finishing. Just a quick critical analysis of the ASTM standards and local design guidelines. ASTM C76, right now it says steel cage for all diameters of pipes. I would suggest the PP fibers may be used up to 375 millimeter, hybrid for the up to 600 millimeter. In larger pipes, yes, we can go with the steel cages. Testing of RC pipes is right now it's continuous loading, so what happens is the loading is being applied continuously, and the operators are busy gauging the crack. It further increases the chances that the error would be more because the loading is continuous. So it is suggested that the continuous loading may be applied until airline crack, but then the loading may be applied in terms of increments. Apply a 2-increment load, inspect the pipe for cracks. Then the earth cover may be reduced to 2 feet. So these are the conclusions. The local manufacturing of concrete pipes requires significant improvement in terms of quality of reinforcement as well as concrete, and the mixture developed in this pipe in this study could be a solution for this purpose. The steel fibers and PP fibers significantly enhance the mechanical performance of the concrete, up to 18% in compressive, and 24% in splitting tensile, and flexion up to 28%. Because of the improvement in the mechanical properties, the fiber-reinforced concrete pipes showed significantly higher crack load up to 58% and ultimate load up to 23% as compared to the conventional reinforced concrete pipes, which is the major benefit of these pipes. Design guidelines, I will just read it to you quickly. So it simply says you better provide PP fibers for smaller sizes. Intermediate sizes, you can go for hybrid of PP fibers and steel fibers, and then larger diameters, you can still go with the conventional reinforcement. Continuous loading rate in ASMC 497 could help. If it is replaced with step loading, it could enhance the accuracy of the work. A few recommendations from this study: the minimum strength requirement, it should be enforced by the relevant government departments, and the fiber-reinforced concrete pipes can be again an effective alternative because of superior structural performance and simplified manufacturing. Double cage reinforcement is still would recommend to be used for the larger pipes, 750 millimeter and larger. And the earth cover may be reduced from 3 feet to 2 feet, the requirement may be reduced. A few recommendations for future work: the in-situ strength of spun cast fiber-reinforced concrete pipes may be investigated by extracting or cutting specimens from full-scale pipes, and the speed of rotation was taken as a constant in this study, could be taken as a variable in the future studies to explore the effect of speed of rotation, because the segregation potential also had to do with the speed of rotation. The potential of single elliptical cage along with PP fibers may be attempted. And of course, the durability and long-term performance, this is required in order to develop further confidence of the stakeholders in these pipes. These are the publications resulting from this study, published in Structures, in Tunneling, Materials, all W category journals, and this is ready for submission in Construction and Building Materials. 2 more research papers are in the drafting phase and hope will be submitted soon. I duly acknowledge Adeel Construction Services for their logistic support on testing of the pipes in NGA City. Hamad Pipe Factory is where all of these pipes were casted. I would thank them for their assistance. These are selected references. Thank you very much.